Hello and welcome to this chemistry lecture series. Today we're going to start chapter 10.3, and now 10.3 and the rest of chapter 10 is going to look a little different than the first two sections. In this chapter, and particularly in this section moving forward, we're going to look at the periodicity of chemical properties. So what we're going to do here is we're going to use period 3 as an example of what happens as we move across the periodic table to the chemical properties of the elements. So essentially what we're going to be looking at is for patterns in how the chemical properties change. And chemical properties is a varied word here, a very definition. But essentially we're going to be looking at how the different reactions that these chemical elements undergo and their compounds undergo is going to change from the left side to the right side of the periodic table across any period. But in this case, we're going to use period 3 as our kind of guinea pig or case study. So an important thing to mention here is that reactions, when we look at them, we're really looking for 4 different things. One is the reactants of the reactions, or which chemicals are reacting with each other. 2 is the products, so what are we getting out of it. 3 is going to be conditions that might be necessary for the reaction. And conditions are a bit different than what we used to look at in honors chemistry, because some reactions will behave differently depending on their conditions. Meaning, is there heat added? So is it a hot temperature or a cold temperature? Is it a high pressure or low pressure? What are the solvents for the solutions? Or even things like, is there a presence of a catalyst in this reaction? And a lot of chemical reactions will change if we change any of those things. And then finally is observations. Now, observations are specifically things that we see during a chemical reaction. So observations could really be one of a number of things. It could be color changes. So because these are changes, don't have an initial and a final, so something like it changes from blue to green, for example. Now, color changes are for solutions or solids. Do not get color changes confused with precipitates. Now, we should be familiar with this word, but remember, precipitate is a solid that is created out of a reaction, usually between 2 aqueous compounds. But essentially anything that when we mix liquids or aqueous solutions and we get a solid, that's going to be a precipitate. Whenever we have a precipitate, we do want to mention the color. So we don't just want to say precipitate, we want to say something like a blue precipitate. And a lot of the time we can put PPT for precipitate. So color changes, precipitate, or bubbles. If there are, I'm not sure, probably do it in a different color. If there are any gases being created during a chemical reaction that happens in a liquid solution or aqueous solution, then you might see bubbles. And bubbles would not really need any more description than that, because we don't not going to say bubbles of hydrogen, for example, because when we ask for an observation, we're not asked for what chemical is it, we're asked for what do we see. And in reality, whenever there's a liquid and a gas is created, what we see is bubbles. Those bubbles do not come with a name tag, that we don't know what they are necessarily, but we will see those bubbles. So these are for observations. As we go through this chapter, this section, you'll learn, actually this whole chapter and inorganic in general, you'll learn more different types of observations. So let's start. So we're going to start with the reactions in this section of the pure elements. In later sections, we'll look at reactions of the compounds of the elements. But in this particular section, we're going to look at the reactions of just the elements. And one of the main reactions that an element can have is with oxygen. Now, as we move from left to right across period 3, from sodium to sulfur, and then eventually chlorine and argon are not going to react with oxygen. So that is a note you should make, that these two compounds do not react with oxygen. But as we move from sodium to sulfur, we see different things. Now, what is one of the main dividing factors between the different types of chemical reactions we see here in this chapter is going to be the types of elements that we're looking at. Sodium, magnesium, and aluminum. Let me not use yellow here. Sodium, magnesium, and aluminum are all metals. So these are all metallic elements, so their reactions are going to be fairly similar. And the sooner you realize things like this, the sooner we see these patterns, the more obvious they become, and the easier it is for us to deal with this type of questions. Because you're not just going to ask about these particular reactions, you will be asked about reactions that are associated with this, reactions that are kind of like a branching off point of these. So for example, for magnesium, we could be asked for this reaction not of magnesium but of calcium, because magnesium and calcium are in the same group, so they'll react very similarly. In fact, chapters 11 and 12 are about whole groups, groups 2 and group 17, and how they react, and the whole column reacts similarly. But here we learn about the reaction of sodium with oxygen. For example, we could really be asked about this particular reaction or any reactions of any group 1 metal with oxygen. Because the idea is that the reaction will be essentially the same, but with sodium being replaced with whatever group 1 metal we're looking at. So we need to start seeing these patterns, not just memorizing what we see, but start seeing patterns in the reactions. So the first 3 elements are metals. Once we get to silicon, silicon is a giant covalent network. So silicon is giant covalent, which is going to give it its own unique set of reactions, or its own unique set of circumstances. So we go from metals to a giant covalent structure to then the sulfur, phosphorus, and eventually also chlorine and argon, which are simple molecular. So these things that we learned earlier in the book or in the year, these are also going to come back, because you got to realize that if things are similar, like here the metals, they are going to react somewhat similarly. So we're going to see that as we go from the metals to then silicon and then phosphorus and sulfur, things start to react very differently from each other. So looking at this, sodium, whenever it reacts with oxygen, and realistically speaking, when we say a reaction with oxygen, we mean burning it. Sodium reacts with oxygen to create its oxide, sodium oxide, Na2O. Magnesium does the exact same thing. Magnesium reacts with oxygen to also create its oxide. The difference is that the oxide of magnesium is 2 plus magnesium, and so it's a 1-to-1 ratio with the O2 minus, whereas the one of sodium is Na2O, because sodium has a +1 charge. So the oxidation number changes here are going to be different for those compounds. This matters because what we're creating is an ionic compound. So here the sodium is going to be +1, and magnesium is +2 because of the charges. In a similar strand, aluminum is going to be a +3 ion. So when it pairs up with oxygen, it's going to make the Al2O3 compound. So notice all 3 of these are doing the exact same thing. Because they're metals, they're reacting with oxygen to form the ionic compound with the oxide ion, which is O2 minus, that they each create depending on their charges. Now, these all do require heat as a condition, because like I said, we're burning the sodium, the magnesium, or the aluminum. And we do see slightly different observations. When we burn the sodium, not only do we see a white solid being formed, which will be the sodium oxide, we see a bright yellow flame. And this is important because sodium creates a bright yellow flame when it burns. That's a very key indication that this is a sodium reaction. So that's something that you should remember. Magnesium and aluminum, on the other hand, they both create a white flame when they react with oxygen. So very different from the bright yellow flame we get from sodium. These also would create white solids, although it's not mentioned in your book. Magnesium oxide and aluminum oxide are both white. So that's another thing we can add in there. So whenever we see these three, again, they react very similarly because they're all metals. Obviously, there's slightly different observations. The compounds they make are different, but they're all just metal oxides, which are ionic in nature. Once we get to the silicon is going to react differently than these three because silicon is a giant covalent structure. Now, with silicon, when silicon reacts with oxygen, again, it burns, and it creates silicon dioxide, which is essentially what quartz is, what glass is, all that stuff. So silicon goes from silicon to silicon dioxide, which is also a giant covalent network. So silicon goes from being a giant covalent network to being a giant covalent network that incorporates the oxygen. Now, there are no specific conditions for this reaction, but something to note, and this really is not something that will be an observation, but a side note here, which is in how space to put it. A side note for silicon is that the reaction is extremely slow. These are very, very slow reactions. Silicon is not very reactive because, like I said, giant covalent network, which means that it's really hard to react and break those covalent bonds. And so it's a very slow reaction. So you should remember that while these are burning, so it's a very fast reaction, silicon is a slow or on the slower side when it burns and creates silicon dioxide. Now let's move on to the simple moleculars. Phosphorus and sulfur, because they are covalent, because they are nonmetals, they are going to form covalent products. When we burn phosphorus in oxygen, what it creates is P4O10. This is a completely covalent compound. This is not in any way, shape, or form oxide ions. This is a completely covalent structure. Now, P4O10 has that phosphorus have an oxidation number of, let's see, this is going to be 20, so these are 5. So this is plus 5 each. So this is going to be phosphorus with a plus 5 because the phosphorus was 0 originally. This is a redox reaction where the phosphorus goes from 0 to plus 5. And the oxygen goes from 0 to minus 2. Now, there's no particular conditions for this reaction, but this reaction does produce a yellow-whitish flame with a cloud of white smoke when it's created. The yellow or whitish flame, again, it's somewhere in between. It's not usually asked about, but just in case you're asked about it, that is the colors to give, a yellow-whitish flame. So moving on to sulfur. Sulfur is kind of unique in this particular set of reactions because sulfur reacts with oxygen to create sulfur dioxide, which is what we would expect. Again, this does require heat, and it's a very pretty reaction. It's a very nice blue flame. We talked about this before in the equilibrium chapter, but sulfur burns with this very unique blue flame that you are probably going to get asked about at some point in your testing. What is the color of the flame that sulfur burns to make sulfur dioxide? And this obviously requires heat because we are burning the sulfur. But sulfur dioxide can further react with oxygen to create sulfur trioxide in an equilibrium reaction. And again, we spoke about that equilibrium reaction earlier in the equilibrium chapter. But when sulfur dioxide reacts with oxygen and creates sulfur trioxide, that means we can actually have end up with two different products for the reaction of sulfur and oxygen. Sulfur dioxide, where sulfur has a +4 oxidation number, and sulfur trioxide, where sulfur has a +6 oxidation number. It depends on how far the reaction goes. Now, if they ask you what does sulfur make with oxygen, you say SO2, sulfur dioxide, because this is a further reaction of that sulfur dioxide. Now, this further reaction is an equilibrium reaction, but it's a very slow one. So we can actually use a catalyst to speed up the reaction, which is a catalyst of vanadium oxide, B2O5. That reaction will speed up, that catalyst will speed up this reaction, making it go much more quickly because, like I said, it's a fairly slow reaction to begin with. So sulfur, very unique here, a lot of things to remember, where it can create a blue flame when it burns in oxygen to create sulfur dioxide when it's heated. And then the sulfur dioxide can further react into sulfur trioxide in an equilibrium reaction, with B2O5 being a catalyst for that reaction. Finally, again, I'm going to mention again that chlorine and argon do not react with oxygen. Obviously, argon is a noble gas, so argon doesn't really react with anything. Chlorine does not react with oxygen. That is not to say there are not oxides of chlorine. There are chlorine-oxygen compounds and polyatomic ions, but they're not made by just reacting chlorine with oxygen. They're made in other ways. So these are reactions of the elements with oxygen in period 3. Let's keep going now and look at the reaction of those same elements, but with chlorine instead. Chlorine is a group period 3 element, so once we get to the end of the period, right, we won't really see the reaction of chlorine with chlorine, but period 3 elements can mostly all react with chlorine. Again, keeping in mind that same division we saw earlier. Sodium, magnesium, and aluminum are going to be metals. I'm just going to put an M here. Silicon is a giant covalent, so GC. And phosphorus as well as sulfur, which we'll talk about sulfur in a little bit. It's all the way down there. But phosphorus is a simple molecular as well as sulfur. So we'll keep these in mind because, again, the reactions are going to be very similar depending on the type of element they are. So, for example, sodium, magnesium, and aluminum all react with chlorine to, again, form an ionic compound. In this case, instead of in the oxide, like it was in the prior slide, these are the chlorides of those elements. But because these are representative elements, their ionic charges don't change. Sodium is still +1, magnesium is still +2, aluminum is still +3. So when they combine with chlorine, they're going to do so accordingly. Sodium forms a 1-to-1 ratio with chlorine because the chloride ion is -1 in charge. Magnesium forms a 1-to-2 ratio, and then aluminum is the weird one, but we've already discussed this. Aluminum is weird because even though we would expect aluminum to be AlCl3, that is the monomer of aluminum. Aluminum creates a dimer with chlorine that we saw earlier in the year. Aluminum creates the Al2Cl6 dimer when it reacts. So even though these are all metals, we do need to keep in mind that aluminum forms a dimer with chlorine, forming that Al2Cl6 instead of the AlCl3 we would expect normally. Now, as far as conditions are concerned, the magnesium and aluminum reactions happen very normally. They don't really need any special conditions. But the sodium does need a little bit of a push to react with chlorine, so the sodium does need to get heated to react with chlorine. There are no real observations for these reactions. They're very aggressive reactions, but there's no real observations we need to worry about. So those are the ionic ones. Let's now look at the giant covalent, which would be silicon. So looking at silicon, looking at the giant covalent element here, silicon reacts with chlorine to form a covalent compound. The covalent compound that silicon forms with chlorine is silicon tetrachloride, SiCl4, whereas the silicon has a +4 oxidation number. And you should be able to see a trend there. Sodium +1, magnesium +2, aluminum +3, and chlorine is going to form a +4 oxidation number, just like it did with oxygen. So we get SiCl4. Again, the chlorine is still -1 here, so that's why it's a 1-to-4 ratio. This is not ionic. Now, remember, I'm talking about oxidation numbers here, not charges. And so this is still a covalent. It's a covalent compound held together by covalent bonds. One other thing to note about this particular reaction and this particular product is that the silicon chloride is liquid in state of matter. Whereas all of the other compounds we have seen here are solid, the silicon chloride is liquid. Now, I didn't mention this before with something like sulfur dioxide, because at this point in time with equilibrium and thermodynamics, you should all know that sulfur dioxide is a gas. But with a newer compound, the silicon chloride, tetrachloride, which we have not seen before, it is important to point out that you do need to worry about these states of matter. So because then you might be asked to put them in. So knowing that silicon is a solid and phosphorus is a solid and silicon chloride is a liquid, you need to know those states of matter as well. Now, just like with the oxygen, the reaction of silicon with chlorine is a fairly slow reaction. And again, this is not so much an observation as it is a side note, because we do not really have a space for side notes. So this is a side note, just like the one for the next reaction, but these are slow reactions. Non-metals do not tend to react with chlorine very well. And so you see that both of the non-metals we have here, silicon and phosphorus, are slow in their reactions. Phosphorus is the last of the compounds we'll see here. Phosphorus reacts with chlorine to form PCl5, which has, again, the oxidation number for phosphorus here is +5. So we see that pattern 1, 2, 3, 4, 5. And again, this is covalent in nature. This is a covalent compound held together by covalent bonds. Now you might notice that the chlorine, there are 5 chlorines on this phosphorus. This phosphorus actually has an expanded octet because it has 5 bonds to the chlorines. Not that it's something that you'll be asked directly for this chapter, but on the AICE exam you might be putting these things together in a multi-part question where one part will be about the reaction and then the other part will be about the best pair theory and of that compound. So again, another covalent compound is formed. So notice ionic, 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 covalent, covalent, and the oxidation numbers increase. So we can see those patterns as we go across the period. Again, PCl5, notice the state of matter. PCl5, just like SiCl4, is a liquid. So that is important to note. There is another compound of phosphorus and chlorine, which is PCl3, which we've seen, I think, earlier in the year. But PCl3 is not the product of this reaction. When you react phosphorus with chlorine, you get PCl5, the more stable of the two compounds. And just like with silicon, this is a slow reaction. That's a bit of a side note. Again, not an ordinary observation because you don't see the slowness, but it's a slow reaction. Now, it should be said that sulfur does form 2 different chlorides, SCl2 and S2Cl2. These are compounds of sulfur that exist between sulfur and chlorine, but they're not part of your curriculum or the reaction to your curriculum. We will see these compounds later on, but their creation through this type of reaction is not part of your curriculum. And just like before, argon is a noble gas. It does not react with really anything, but nothing not chlorine. All right, so that's the reaction of the period 3 elements with chlorine. Let's move on to the reaction of the 2 first elements in period 3 with water. because the first two elements, sodium and magnesium, are known as what we call active metals. Active metals react with water, and they're very reactive metals. Group 1 elements, group 2 elements are considered to be active metals, and so they have very violent reactions with water. And as we go down that group, those reactions get more violent. We'll look at that in chapter 11. But for now, let's focus on just these two. The reactions of the other elements with water are not going to be something we look at directly, and you'll see why in the next section. But let's look at the reactions of these elements, these two elements, with water. Sodium reacts very straightforward. When sodium reacts with water, it creates sodium hydroxide and hydrogen gas. It's a very simple single replacement reaction, whereas the sodium and the oxygen come together, and essentially the hydrogen in the water is replaced with that sodium. That's why it's a single replacement reaction. We create the sodium hydroxide because when we look at the water, what we should be picturing is not H2O, it's HOH. So the hydrogen gets replaced, and I'm going to change my arrow here. So the hydrogen gets replaced with sodium, and the sodium ends up pairing up not with oxygen but with OH, with hydroxide. So that's where we get that sodium hydroxide from. And then two of these hydrogens, that's why we need two of these, end up creating the hydrogen gas. So very straightforward reaction here. Water with sodium makes sodium hydroxide and hydrogen gas. This does not need any special conditions. You throw a chunk of sodium into the water and they will do this. Now, there's a lot of observations. This is one of those reactions where we see a lot of things that we need to know here. First, the sodium melts. But a better word than melt, although it is melting because of the heat, it's a very exothermic reaction, is that it disappears. So sodium melts, sodium disappears, it shrinks and disappears, any of those things. But before it does that, the sodium is going to float. Because the hydrogen is created underneath it when in contact with the water, it creates a bit of a bed. So what happens here is that we have and I'm going to draw a picture here, a very bad picture, but I'm going to draw a picture. So if we have a beaker or any kind of container full of water, and we pop a piece of sodium on this water, what's going to happen is that the sodium is going to sit right on top of the water because hydrogen gas is being created when the sodium contacts the water. So there's only hydrogen gas bubbles being made where the sodium is coming in contact with the water. That hydrogen gas is going to keep that sodium from sinking. It's going to keep it floating. As this reacts over time, the sodium is going to become smaller. And there's going to be less hydrogen gas being made underneath it because we have less of that reactant. So rates of reaction, right? We talked about that. This rate of the reaction slows down, and eventually the sodium is going to be very small and sink to the bottom of that water. Once it sinks to the bottom, it's still reacting though, so we still get those bubbles of hydrogen gas. But most of the time we don't see the bubbles because the hydrogen is essentially floating on top of those bubbles. And what can happen sometimes, and happens actually fairly often, is that sodium will catch on fire. And that's because hydrogen gas is flammable. Hydrogen gas is flammable, and this reaction is very exothermic. So as the hydrogen gas is being created, it lights on fire because of the heat given off by the reaction, creating this kind of like fireball effect around the sodium. So it's a lot of different things. So the sodium first floats above the water. So first the sodium floats. It slowly melts or shrinks over time, creates hydrogen gas that catches on fire, and then it sinks as it gets smaller and there's less hydrogen gas being created. So it's a whole series of events that happens with this reaction. So going back, those are some of the observations we have with the sodium. Now magnesium is a bit different. Magnesium reacts very differently with water versus with steam. Now, as we all hopefully know, water and steam are both H2O, but water will be a liquid H2O where steam is gaseous H2O. And this is what I meant before by conditions matter. Because even though these are both reactions with water, they give off different products. The reaction of magnesium with water, with liquid cold water, is the same as with sodium, as we would expect. Instead of magnesium, we have instead of sodium, we have magnesium, but it still creates that metal hydroxide, in this case magnesium hydroxide, MgOH2, and hydrogen gas. Now, the reaction of magnesium with water is extremely slow. It is a very slow reaction. Again, this is a side note because speeds of reaction are a side note, not really an observation. And what we see is very small, slow bubbling. So we see very small and slow bubbles coming out of the magnesium as it slowly reacts with water. And those bubbles are of hydrogen gas that's created. Now, that changes though when we use steam instead of water. If we use gaseous water, if we use steam, which by definition is hot, so one of the conditions is going to be heat here, we don't get the magnesium hydroxide, we instead get magnesium oxide, which is a solid and the hydrogen gas being created. The observation here is a white solid is going to form, and that white solid is going to be magnesium oxide, but you have to be careful because you're going to want to say that there's bubbles because hydrogen gas is created. But this reaction does not have bubbles because there's no liquid in the reactants. Formation of bubbles requires a liquid. Gases can be created without bubbles being created if there's no liquid to capture the gas in that bubble form. So when magnesium reacts with steam, magnesium oxide gets created, which is a white solid, and hydrogen gas also gets created. But that hydrogen gas does not come out in the form of a bubble because there's no water. There's no liquid at all to bubble through. And so this is just gases being created. So instead of the bubbles, the observation with steam is a white solid. Now you couldn't memorize this, but if we look at the reaction, if you remember the reaction, it just makes sense. We do form a gas, but there's no liquid, so no bubbles. And then magnesium oxide, like most group 1 or 2 oxides, is a white solid. So that's the only observation we see is a white solid being formed. Now both reactions in the liquid water, right, result in an alkali solution. Remember, alkali means base that is aqueous, a water-soluble base. In this case, what the alkali is the hydroxides, because hydroxides means basic, right? And both magnesium hydroxide and sodium hydroxide are water-soluble bases because they have hydroxides in them. And so these are both going to form, both of these reactions are going to form alkalis, sodium hydroxide and magnesium hydroxide respectively. The sodium hydroxide solution is more alkali than the magnesium hydroxide solution, and that's because while sodium hydroxide is highly soluble, let me write that on here, as far as solubility rules, this is highly soluble, meaning it all dissolves in water. Magnesium hydroxide is only slightly soluble. So not all of the magnesium hydroxide dissolves, not all of the hydroxide is released, and therefore it's not as basic. So magnesium hydroxide is only slightly soluble in water, making it less basic. Meaning that this reaction has a higher pH, more basic, than this reaction, which has a lower pH, less basic. Still basic, just not as basic as the sodium hydroxide is. All right. So this is another side note that you're gonna have to remember about the basics or basicity of the two reactions with water. Again, the last one, we don't talk about its basicity because that will require solutions, require aqueous solutions, which we do not have in this last one. That is it for section 10.3. Hopefully this gave you a good look at how to discuss and look at inorganic chemistry. And I'll see you all again in section 10.4 in the next video.